Thank you for the introduction. My name is Zhuohang Li. I'm a first-year PhD student at the University of Tennessee, Knoxville. And today I'm glad to present our work, Practical Adversarial Attacks Against the Speaker Recognition System. This is a joint work with my colleagues Hong and Yi, my advisor, Professor Liu, and Professor Yuan and Professor Chen from Rutgers University. So speaker recognition is the task to identify the voice of a given audio from a set of enrolled speakers by selecting the one with the highest score. And it has been widely applied in many security or privacy-sensitive applications. For example, smartphone manufacturers like the Samsung allows their user to use their voice to unlock their phone by just saying, "Hey, Bixby." And also, applications like WeChat allows their user to use their voice to log into their account. And commercial banks like Chase and Wells Fargo also use voice print to identify their user whoever are calling to inquire about their account. And this not only increases security, but also allows their user to receive services more quickly and easily. And also, corporates like the voice biometric group use voice for access control. So recent study found that applying deep neural networks in the speaker recognition can actually increase accuracy. However, it has been previously showed in the computer vision domain that deep neural networks are vulnerable to adversarial attacks, especially in distorted input that can fool the DNA models to make false prediction. For example, in this case, we have some small distortions, and after adding the distortion, human would still view this image as a panda. However, DNNs would misrecognize it as a gibbon. Another example is that an autonomous vehicle maybe successfully recognizes the stop sign, but by applying a few stickers, it will be misclassified as a speed limit 45. So this adversarial attack has posed a severe security threat against the DNN-based speaker recognition models. And before we talk about those attacks, let's first take a look at the speaker recognition pipeline. And we have an incoming audio, and it will be first picked up by the microphone, and then processed by the model, and finally classified as the corresponding speaker. And for our conventional attacks like the replay attack, synthesis attack, and the voice conversion attack, those attacks are very robust, and they can be injected through the physical channel. That means they can be played from a nearby hidden loudspeaker. However, those attacks can only fool human. And in modern speaker recognition models, they are usually embedded with the defense mechanisms that can detect and defend such attacks. Adversarial attacks leveraging the adversarial example are a stronger type of attack, and they can even fool the state-of-the-art speaker recognition model. However, those attacks are very sensitive to the over-the-air distortions, for example, the reverberations and the ambient noise. And therefore, they only allowed to be injected through the digital channel. That means they assume that the generated file is directly fed into the model without being played over the air. So in our work, our goal was to design a practical attack, adversarial attack, that is strong enough to break state-of-the-art models, but also robust enough to be played over the air. So our contributions are listed below. To our best knowledge, this is the first work of designing a practical attack against the multi-class speaker recognition systems. And we utilize the estimated room impulse response to make our attack practical. And also, we applied gradient-based adversarial machine learning algorithms to make our attack unnoticeable to human. And finally, we evaluate our attack on a large dataset containing 109 English speakers. So now let's take a look at the threat model. So imagine when a legitimate user tries to pass the speaker recognition model, and normally his voice will match his profile, and he can be successfully recognized. However, an attacker can try to inject some adversarial noise through a nearby hidden speaker. And in that way, the legitimate user will be misclassified as another speaker, and the authentication process will fail. And this is called the untargeted attack. And another situation when an imposter tries to pass the speaker recognition system, as he does not have access privilege, he cannot pass the system. However, he can try to embed some adversarial noise to make himself recognized as a legitimate user with the access privilege. And in that way, he can pass the speaker recognition model using another person's identity. So this is called the targeted attack. So to verify our idea, we choose X Factor as our target model. X Factor is the state-of-the-art DNN-based multi-class speaker recognition model. And it has 3 components. So given an input audio, we first extract its male frequency cepstral coefficients, and then we use a DNN-based embedding model to map the high-level features into the lower dimensional embedding space where distance directly represents the speaker similarity. And finally, we use a probabilistic linear discriminant analysis to classify these results. And we assume a white box setting where the adversary has complete knowledge over the model's architecture as well as its parameters. This is commonly used in previous studies as well. And to formulate the attack, we denote the input audio as x, and the x vector model as a whole can be viewed as a function f, which maps x into p, where p is the output probability vector. And therefore, the untargeted attack can be formulated as we want to try to find the minimum distortion delta such that the adversarial example is misclassified. And for the targeted attack, we want to find the minimum delta such that the generated adversarial example can be misrecognized as the desired target speaker y sub t. So here's the overview of our attack. Our goal was to generate adversarial examples that can fool the speaker recognition model after being played over the air. And we have the untargeted attack and the targeted attack. And in both attacks, we need to consider the estimated room impulse response to make the attack practical. So what is room impulse response? Room impulse response models, denoted as h of t, models the transfer function between the played audio x of t and the received signal y of t. And this sign here denotes the convolution operation. And to physically measure this room impulse response, we need to first play an excitation signal, and then we record the corresponding response signal. And the room impulse response can be estimated by convoluting the response signal with a reverse filter. And we conducted some preliminary experiment to verify this RIR estimation. We use an excitation signal ranging from 20 to 20 kilohertz with a duration of 5 seconds. And then we play and record some speech audio samples, and we compare the actual recorded signal with the predicted signal using our estimated RIR. And as we can see from here, those two spectrograms are very similar to each other. And we also used, to quantify this similarity, we also used the mean square error. And as we can see from this result, our RIR estimation is very accurate. So now let's talk about how to generate adversarial examples. So previous studies have shown that due to the local linearity of DNN models, linear perturbation is sufficient for generating untargeted adversarial examples. So here, the x prime denotes the adversarial example. It is constructed by applying a noise delta to the original input x, where delta is calculated by taking the sign of the gradient of the loss function with respect to the input x. And the epsilon here is a pre-chosen constant that is related to the attack strength. And we use cross entropy as our loss function. So pulling those things together, we get the digital untargeted adversarial example given by this formula. And to make our attack practical, we need to inject the estimated room impulse response h into this formula. And now for the targeted attack, it can be modeled as an optimization problem. We want to minimize the distortion delta such that the generated adversarial example can be recognized as the target speaker y sub t. And as directly solving this nonlinear constraint problem is very difficult, we instead solve its Lagrangian relaxed form. And we apply gradient descent to find the optimum delta star. And then the digital targeted adversarial example can be generated by applying delta star to the original input. And similarly, we need to consider the room impulse response h to make our attack practical. What's going on? I'm sorry. So to evaluate our attack, we use a public dataset called VCTK corpus. So it contains over 44,000 utterances from 109 speakers. And we separate into the training and testing set with a ratio of 4:1. And we choose a pre-trained X factor model provided in CALDI as our baseline model. And we have three evaluation matrices. So the first one is the speaker recognition accuracy, which shows the percentage of utterances being correctly classified by the system. And the attack success rate is the ratio of succeeded attacks over the total number of attack attempts. And we measure our distortion in decibels. So here is the results of our digital attack. As we can see, if we do not perform any attack, our baseline system accuracy is around 92%. But as we increase our attack strength at this point, we can reduce the system accuracy down to only around 2% with an average distortion of minus 29 decibels. And for our targeted attack, it is evaluated on all original target speaker combinations. So that means for each speaker, we generate targeted examples targeting at the rest 108 speakers. So that gives us a total number of 109 times 108 pairs. And if we use an attack strength of 0.2, we can get an attack success rate of 86%, with an average distortion of minus 32 decibels, which is approximately the difference between the ambient noise in a quiet room and a person talking. So we evaluate our practical attack in two scenarios, the office and the apartment. And in both scenarios, we play and record 10 pairs of digital and practical adversarial attacks examples. And as we can see, if we do not consider the room impulse response, the digital attack can only succeed once in the apartment setting. Well, if we consider our room impulse response, our practical attack can guarantee a 50% attack success rate in both settings. So now let's hear some audio samples. I hope this plays. So in this case, we try to make speaker number 1 recognize as speaker number 20. And here's the original audio.
Every time I play, I do not.
And here's the generated practical adversarial audio.
Every time I play, I do not.
As we can hear, the distortion is very subtle, but we can make it misrecognized as speaker 20. And here's what speaker 20 really sounds like.
The second goal was equally impressive.
So the voice is quite different, right? So in conclusion, in this work, we designed a practical and systematic adversarial attacks against the X factor. And we applied gradient-based adversarial machine learning algorithms to launch both untargeted and targeted attack. And we integrate the RIR estimation into our adversarial training process to make our attack more practical. And we conducted extensive experiments in both digital and real-world settings, and the results verifies the efficiency of our attack. So that's all for my talk, and thank you so much for listening. I'd be happy to take any questions.